All right. Today, we're going to do, so we're still on time evolution. Actually, probably till next Wednesday. Today's lecture and 2 more. That's probably how long it will take us to finish up time evolution as we're doing time evolution right now. What was I going to say about this? I already forgot it. Anyway, we're doing time evolution. I just want to remind you that we started with this. If the time evolution operator has it has the Hamiltonian in it, and if there is time dependence to the Hamiltonian, which there would be in the case of like modeling light as like just like a cosine electric field, then that would be a time dependent Hamiltonian. And we won't get into that problem in this class, but it is a thing that that people do. So I just want to remind you of the way we did this, and I'll stop here because it will be our starting point for something else. Okay, so we're looking for this, right? Remember, we're looking for a way to propagate. Oh, it gets a little hat, right? It's a little hat. So U, of course, is a unitary operator from the time-dependent operator. It's for any unitary operator, which there's a lot of unitary operators, including the translation operator. Often, when I read papers, sometimes they'll just start writing about U, and I just know that they're talking about the time evolution operator. Okay, so we're looking for this. Now, I know what this is. This is taking, I didn't use T0, but it's arbitrary. This is just advancing, just a very small amount of time. And this is probably, some dt amount of time. This setup is the reason I think that the book uses this weird notation of t comma t0, and later we'll just make t0 0, and then we just won't write it at all. So heads up. It's just, I find it kind of awkward notation, and the book then changes the notation. But the reason that they use what I find to be somewhat awkward notation, writing t0, and we all know it should just be 0 seconds, is because it actually makes writing this a lot easier. So I set up the time, the very small step time evolution operator like this, and then you end up with a differential equation. And let me remind. So from there, we solved. If the Hamiltonian has time dependence, therefore what you solve is a Dyson series, which no one actually uses. We can do a time-dependent, I know some cheap and easy ways to do time evolution, even with time-dependent Hamiltonians, that may have error, like the algorithm, it'll be on computer, the algorithm has error, but I don't find it to be so bad that the numbers are, that is like junk. It comes out okay, in terms of like what I'm trying to do. Now, if the Hamiltonian is not time dependent, so I'll just put it that way, you can actually do it this way, the same way that we did. Your book actually expresses this. The version that you may find on the website, the update, so there's 2 authors on that one, and so the second author updated it so that it was a little bit better. That's why I put that one. That's why I put that one for you. And again, here is where I'm talking about the awkwardness of t minus t naught instead of just saying I h bar. Again, you usually just see I h bar t because t naught is 0. Okay, so if you just raise this to the n, and then of course the limit of n goes to infinity. This is just an identity for an exponential. So now recall that what I had actually done is I had solved this Dyson series thing, which I told you In my 20 years of doing this professionally, I have been to one talk where someone once mentioned a Dyson series. It's the only time I've ever even seen it mentioned. Just saying. But I'd taken that, and then I went from there to here, but I could have also just done this. And that's what your book does. That's the one thing actually I appreciate, the update to the book by the other guy who's the author. Okay, and as I mentioned, that often the case, application of this thing is kind of easy. So I want to just review one thing that's in the book. It's kind of silly, and then what we're going to do is apply this to a couple of situations. The thing that's going to be kind of difficult is that the application of this operator is really easy when it's applied to an eigenstate of the Hamiltonian. It's just e to the I energy, t, right? It's unbelievably simple, like the question on the homework. E to the function of an operator is just e to the function of the eigenvalue of that operator. This is technically a function of an operator because it's multiplied by constants, which is the easiest function imaginable, right? So anyway, so it's going to start out kind of easy, but I'm going to have, situations, this commutes, this doesn't commute, yada, 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 where it can get kind of confusing about what's what, why the results are different. Okay, I did want to mention one thing, and that's actually just to drive this thing home. All right, now what you do from here, and again, I won't write all this out because I did it last time. What we found was you can do this. So remember that if I multiply this by 1 and I bring it over here, divide by dt. So this is basically like the next step, and if I just carry on over here, which is what I did last time. Okay, if I do that, then what you do is apply a state, and we will make this a non-time evolving state. So remember, that is the correct notation for a state like we've been doing it from now. So instead of trying to figure out what the operator is, not that I haven't, we did that last time, let's just let's go from here, not worry about the operator, let's just apply a state to both sides. So what you end up with is still a function of an operator, always act on the left of the ket, and two operators is an operator. I don't remember if I'm assuming H is time independent or not. Okay, so that's stupid. Okay, this ends up being, it turns out that, actually I have to admit, this slightly confuses me now that I'm looking at it. I have to admit now I'm slightly confused. Okay, again, using the notation, that will change it a little bit because we'll just drop T0 once we get into some harder problems. Okay, so we've just dropped, so whereas before our goal was to solve the unitary time evolution operator, now I'm evolving a state. So, and now the operator's gone, so I just assumed that I knew what it did. And what it does is it evolves a state. It evolves a state forward. Okay, then to get to our sine pi x over L wave functions, you're going to project. So that's the correct word. Remember I was telling you that bras are a little funkier. Kets are easy to understand, they're states. Bras are funkier. But it's always think of them as, they're not really, they are, but they're not states, they're projections onto states, including the X state, which has its own issues, right? Okay, what do you get from here? I guess it just passes, so this is something that also bothers me a bit. One of the things you have to be careful of is letting things just pass through. operators that generally we can't. And derivative is an operator, so this bothers me a bit. I just let the x pass through. And now what I'm going to do is I'm also going to make the Hamiltonian very generalized, because that's my minimum operator. And as usual, we always, it's a little subtlety, but I don't know how many people, have you ever noticed this? Potential energy is almost always a function of a position. It's not a function of a velocity. It seems like it could be if you're talking about like viscous forces, like drag or something, but really, I've never seen potential energy being anything other than a function of position. And of course, we're going to keep everything in the x dimension. There we go. Now we know what, now one of the damnedest things about, remember how I mentioned what momentum does with kets? It's kind of like, actually maybe it's okay here. Remember that it was this, let me move aside. And remember I said this was really weird. Oh, wait, sorry. Okay, sorry, it's got to be perfect. There we go. Okay, so remember that the momentum operator in Dirac land is a funky beast, because it allows that, remember I was saying that you can't just be sliding kets and bras around just arbitrarily, but the very existence of the momentum operator is to allow that. This isn't like a derivation, it's a definition, and we proved it. So that's probably why I'm able to slip this through this derivative. I'm not too sure, but here what I'm going to do is, and by the way, so this is the time-dependent Schrodinger equation, and I'm actually done with it. Did I say, I'm sorry, that's T, right? That comes from the definition of the time evolution operator. My bad. So I'm just writing this over again, but I'm making a bit of a mistake. Okay. All right, notice that again, with position on the left of the momentum operator, and this is just a function of momentum operator, you can allow x to slip past it. So that means that and of course the derivatives are still here, and I'll use del squared to represent the two derivatives. So that's a double derivative with respect to x. Okay, now, if the potential energy is a function of x, and x is Hermitian, then I can just operate on the left side and then just say that this, oh, we get to have it's an operator, that this is then just a function, it's no longer, no, wait a minute, no, I can put the operator there, I don't actually need that. It's redundant to put it twice, right? Because x is an operator. Okay, so again, this can actually operate on the ket, on the bra. You normally need an adjoint, but this would be Hermitian because the operator of position is a real thing, right? It gives me something that's measurable. I don't care what the potential energy is something measurable. If it's measurable, then the operator inherently has to be Hermitian, and so it can operate on kets or bras equally, because it's equal to its own adjoint. So what that means is that x inserts a value, and then it can jump past it to give me this. So my point here, my very long-winded point, is that, you often see people do stuff like this. You go from here to here, and all the operators are on the left, and then you've got a wave function on the right. My point to you is that while this is fine, don't take it for granted, right? So that's one thing that kind of came up in the last homework was you can't just be rearranging things arbitrarily. And that may seem like you're just like, oh, screw it, through it. I'm just going to pass this right through here because it looks like my undergrad stuff. And that is correct, but there is a good reason why this works the way it does. It's all legit. With this really being the only funky thing, that the operator's job is inherently to allow the bra to skip over it. And again, that's a very strict, this is the only thing I see, the only operator that allows a bra to jump over it. It's the only one that I know that does that. So that's a really weird one. Anyway, so notice that this is actually the time-dependent Schrodinger equation. Okay, so your book mentions this. There's a couple of times the book says, oh, we're going to derive the Schrodinger equation, time-independent, time-dependent. And the thing is that it's still a historical anomaly. I looked this up. That Schrodinger publishes 1923, something like that. And he actually used, I found it's all in German, but I found the papers. You know, a library's pretty good. And it's all in German, but you can tell that it's on the hydrogen atom because that's what everyone was working on. And that's actually a pretty hard one. So Schrodinger discovers the Schrodinger equation and does the hydrogen atom. So that's something. The thing was that everyone then started following up on it because how could you not? And no one thought to ask him how he came up with it. He just wrote it down. And then he died, and no one knew how he came up with it. So they had to try to reverse engineer it. So that's why I think you see this being done. At the same time, though, again, this is something, not that it matters really, but I just want to point this out. I think that's deeply disingenuous. The reason is, when I did this, and I said that this is the time evolution operator, remember, I said this is 1 minus I times some unknown operator, and by the way, the operator is the Hamiltonian. I had some justification from that from Poisson brackets. But really, I just said, this is the time evolution operator U, and U is this. Reality is that itself is reverse engineerable from the Schrodinger equation, right? If I can go from here to here, then I can go from here to there as well. So as much as it may seem like, oh wow, look, I finally seen a derivation of the Schrodinger equation, when I did something like this, which I really did not have any good reason to other than I'm just saying this is what it is, I fixed the result. It had to work out because I made the particular operator here, I made that the Hamiltonian. So there's my dt, there's my Hamiltonian. Remember, that dt, and that dt right there, those are the same thing. Anyway, so I just see this kind of stuff, and like I say, I think they're being disingenuous because it comes from here. And this, I really just wrote it down, right? And so remember that there's a paper. I have a paper. The stuff I talked about on the first day, I got from a paper that I put on the website that talks about the historical underpinnings of Schrodinger's equation and gives a derivation based on Maxwell's equations, which they think that's how we did it. So anyway, and it's a bit more complicated than all of this. Okay, so now I'm going to apply the thing. And we're going to do a lot of stuff that's going to be pretty trivial and easy, and that's cool. But then I'm going to make it kind of hard, a little bit harder. The problem is understanding the nuances between the situations that it goes from easy to hard. And that doesn't mean anything until you see what I'm talking about. Okay, so what we're going to do is now we're going to apply. We're going to apply the time evolution operator to a bunch of situations. And of course I'm going to apply it to states. So I'm going to apply to, let me just, the state is a ket. So I'm going to apply it to some kets. And remember, the whole point of quantum mechanics is ultimately to get expectation value. So I can time evolve a ket, whatever. I'm going to take that ket and apply it to an operator and then square it, because that's ultimately what the only end result is, that, because it's the only thing we can measure, our expectation values. Complex conjugate times the thing. Okay, so let me see here. Okay. Now again, so I'm going to have some operators. I'm going to have an operator A, and of course we're not doing time-dependent quantum mechanics without a Hamiltonian, so you have to know what that is. Okay, and we're going to assume this. Assume that the operator and the Hamiltonian commute, and note that, and I'm going to use the typical A dash ket, which is an eigenfunction of the A operator, whatever the hell that is, doesn't matter. And of course, if A, one of the things is when I go to talks or read papers, what slays me is they're like, the operators don't commute. What the hell does that mean? I mean, I know what it means. I know that means that this is not zero. The problem is, I mean, I get that, and I know that there's consequences. The problem is that there's like a zillion freaking consequences. So when papers use that highfalutin language, that's like saying time goes forward. Yes, so what, right? So anyway, so I see that all the time, and it drives me nuts. So of course, the Hamiltonian operating on this A state gives the energy of that state. So it's times the state, right? So it's that's the eigenvalue equation working out correctly. Okay, now let's. Okay, so this is another example. So I'm getting this from the book again, but let me again point out something that's a little disingenuous. Let me work over here. Okay, so what I'm going to do is I'm going to put the time evolution operator in this t minus t naught thing again. I'm telling you it's going to go away because we're going to make t naught 0. But for now, it's in the book, so I'm just going to keep it. Okay, let's write it in matrix form. Any operator or assumption of operator can be matricized. And actually, I really do like matrices because I do find them easier to work with, especially all that spin stuff, right? Now, again, there always has to be two resolutions of the operator. One generates the columns and one generates the rows, right? So A to the n, outer product, A to the n, operator. And I need to give myself lots and lots of room. I hate this little h bar on the bottom. That one always bothers me. A to the m, outer product, A to the m. No, what the hell is that? Little dash. There we go. Okay. Again, operates on this. It's always kind of fascinating to think of e to the derivative, to think that that's a thing that you can do. I have to write all this stuff down again. I'm seeing that there's like computerized versions of this where you basically can PowerPoint, but it looks like it's a blackboard. That's kind of neat. And there's not much to do here except write e to the minus I, e to the a, and t minus t naught. A to the m, right? I'm acting on the right, so whatever the hell this m is. There we go. All right, now, again, I've been blabbering on and on about just be careful when you start moving things into and out of kets and switching operators. Anyway, yeah, it was the thing that came up on the last. I'll give a couple more examples, but here, let me finish this up. Okay, in this case, now this e to the I is a number, and it can be moved around. It can be put in front or behind. It doesn't matter. It doesn't matter where it goes because it's a number. And now I've got a delta function. And here we've got this number that is not really a big deal. And now that I've got a delta function, because I've got the a to the n, a to the m, of course we all now should jump that these are a delta function. Kronecker delta function. Dirac delta functions if it's x or p. Kronecker delta functions when it's like plus and minus when we're talking spin states. This looks like a spin state problem, right? Because I'm using sums instead of intervals. I guess it could have been x, but this is easier. Okay, now remember that what I got to do is I got to choose. I'm going to wipe out a sum, which is awesome. I like getting rid of stuff like that. And then I choose to either make all the n's m's or all the m's n's. And I'm going to make all the. I've been using n a lot, so I'm going to keep n and get rid of m. And that means that all of the, anywhere I write and M, I now write an N. So that M is now an N. Oh, and now I have to get rid of this because there's not enough room. I messed up. Now check this out. I have to write A to the N now, right? That's a subtlety. That doesn't look good. It needs to look good. There we go. Okay. E A to the N. Okay. All right. Now that's it. That's the time evolution operator. It is the important of this is it is diag. So another thing is you got to get used to the terminology. It's diagonal, right? Because so in matrix form, the time evolution operator in the basis of a state for which is an eigenstate is diagonal. Now, the thing is that kind of slays me about this. The book does this, and it's like, oh, okay, we've already covered this. I don't know why the book does this. We've already covered this. Remember, we said an operator, when acting on in the basis of its own eigenstates, an operator is diagonal. Okay, now if that sounds a little highfalutin again, sorry, I'm kind of going from left to right, which is weird. Look at SZ. In the basis of its own states, it's diagonal. Oh, there's a little H bar. Right? In the basis, in the SZ basis, it's diagonal. So we've already covered this, in SX or not. But SX, the SZ plus and minus states are not okay with SX, and that's why SX has off diagonal. Anyway, so we basically already, we've already talked about this, we've already seen this. Now we applied the time evolution operator, found the same thing. I guess the only difference, the only subtlety being that we weren't applying the Hamiltonian, but a function of the Hamiltonian. But that never matters. One of the things also to remember that functions of operators in terms of their properties, do they commute, are they diagonal, it's all the same as whatever the operator is. And you can write out Taylor series and all that jazz to figure that out and whatnot. Oh, and the first question on the problem set, that's kind of an interesting one, because I'm going to move on from here and do a way more interesting problem. You know that we're often in a situation, like when we go from here to here, where you just write out the Taylor series of the operator, and then it operates and it gets an eigenvalue, and then you end up with the Taylor series of the eigenvalue that, hey, guess what, happens to be the same damn thing, right? On problem one, I'm actually going to have you prove that. So again, you write a Taylor series out, you go to like 3 terms, you see how it's going to go, and then you just say, oh, well, obviously this is going to turn into a Taylor series. But technically, you need to write out an infinite number of terms to prove it exactly, right? If you don't write an infinite number of terms, which would take a while, then you haven't really proven it in a pure mathematical sense. So if you want to prove that this is that, the way to properly do it is part of question 1, which I like to show you that, because that problem is it's a little awkward. But it's how you actually do those kinds of proofs. And then, by the way, the proof is to show that the derivatives are equal. And apparently that does it. Anyway. All right, so this is kind of a waste of time. I just wanted to do it because the book did it. And, reinforce some previous lessons. But now it's going to get more interesting. Now it gets more interesting because we're going to talk about the states themselves. So another thing we're doing is, we're working with states that are evolving in time. And as I mentioned, next lecture, we're going to work with operators that evolve in time. So that's coming up next time. Okay, now, so A and H commute. And we've done some stuff with that. Okay. Now, if you were to solve this, and let's evolve it in time. So another thing is get used to that. What you find is So remember, let's do that for this state. When we do expectation values, you have to pick a state. You can't just say in general. That doesn't make sense in general. Expectation values, you know, if this is like the expectation value for position for harmonic oscillators, sorry, that's a bad example. X squared for harmonic oscillators, it depends on what state you're talking about. X for harmonic oscillators is uniform, it's always 0 no matter what state, not X squared. Anyway, all right. So if we do this, and let's time evolve them. All you get is this operates on that. All right, so remember this is the time evolved state. And let me not write T naught. Now remember I was always saying you have to be careful. That's positive, right? That's positive. You had better be because these have to cancel. And again, I'm not going to write T naught because that sucks. Now that these are numbers, now they can cancel each other. So again, another one of the things I wanted to bring up, unitary operators, they cancel each other, right? Otherwise they're not norm preserving. Otherwise the time evolved state could lose its normalization, which is to say it literally disappears into another universe, which only happens in TV shows. So you can't just be rewriting these things, you know, you can't just arbitrarily change the order of operators, like ever, because in every one of these situations you could have one of them leap over the other and get canceled out. No, not good. If you know that these commute, you can, or if you're working on this situation where the state is an eigenvalue of the unitary operator, in this case the time evolution operator, now you can. Now these can cancel. It's e to the I times e to the minus I, basically. Okay, so the expectation value over time is equal to the expectation value of the state not evolving in time. It doesn't matter. It doesn't change. Okay. Okay, so let's make it harder. B does not commute with H, B does not commute with A. That, I think one implies the other, by the way. I'm not too sure if it could commute. If B does not commute with H and A commutes with H, then I'm pretty sure B cannot commute with A either. Like, there's some identity. What you find, and I won't even do it, the expectation value of B over time is still, guess what, going to be this. The same thing happens, just change the letter A with B. No T. So in other words, even if the operator doesn't commute, again, just put a B here. It doesn't matter because the action is happening over there. And what you get out of this is for an eigenstate of H, nothing changes with time. Nothing changes with time. Expectation values, whatever. Everything is time invariant. Okay, and that's actually one of the most important things I could ever tell you. So take a hydrogen atom. What's the ground state? It's a 1s state. Okay, does it evolve in time? Given what I just said. Right? No. Right? It's not doing anything. Right? Anything, there's nothing you can calculate that it's actually evolving in time. Okay, now, does the universe have a lot of hydrogen atoms? And I know a lot of it's H2, but I'm sure that there's some H atoms that didn't find a partner, so they're just floating around, right? Lots of free hydrogen atoms. Okay, is the universe doing stuff, or is the universe completely static? It's doing stuff. Well, that's not consistent with this picture, is it? How do you resolve that? Again, now, I'm assuming that the universe is mostly hydrogen atoms. That's a little bit of a stretch, but I don't think it's much of a stretch. So either the universe is mostly static and doing nothing, or this is wrong, or there's an interpretation problem. As I said, what I just said is not, they both can't be true. So here's the trick. And I can prove that in a second. Hello?
I need help, please. Sorry.
Huh?
Do you know where is Adam's house?
Adams? Jane Addams' house?
No, Adams Hall, it's one of those small,
The
discussion.
African American Culture Center.
You see that building, like, that I'm pointing to, like, directly that way? It's one of these two. I think it's either one of these two or it's on the other side of the quad.
Yeah, thank you so much.
Why not? Anyway.
X that out.
Maybe I'll just cut that out. Anyway, okay, so it turns out that for the universe to be dynamical, for me to do this and the cats to run around the house, they're not in their ground state. Nothing is truly in the ground state of the Hamiltonian. So that means that an H atom wave function cannot be the 1s state. It cannot be purely the 1s state. So let's make it, it has to be some kind of coefficient plus some other coefficient. Let's say it's a 2p, right? Let's make it spectroscopically allowed. Okay, so here's my point. If hydrogen is in the 1s state, and you would think that most hydrogen would be in the 1s state, remember it takes a lot of energy, light energy. Let's again make it easy. Remember that if you absorb a photon from a 1s state, you'll be with 2p because of angular momentum, blah, blah, blah. Anyway, it turns out that for anything to happen, nothing can actually be in a ground state of the Hamiltonian. Now, this is one solution, and I'm going to show you a little bit more of this in a minute. However, my problem with this, I have actually a problem with this, which is that a 2p state for hydrogen is kind of high in energy. That requires, so if I take a UV vis spectrum of hydrogen atom gas, the first absorption is at 91 nanometers, which if you were ever exposed to 91 nanometers would give you instant major cancer. That is super high energy. And then of course, more excitation is even higher in energy. So I contend that this is reasonable, that I know that this is a dynamical state, this can do stuff, but implies that hydrogen is also walking around with a lot of excess energy, which is also a little hard to swallow. Okay, now here I want to point out that I've written states of the Hamiltonian of the electron. Are there other Hamiltonians? So notice that I've only, when we talk about 1s and 2p states and 3d, this, that was something that came out of the Schrödinger equation when the Hamiltonian had the kinetic energy and coulombic energy of the electron. Is that all? Is that all there is? Now I mentioned the photon. Where's the photon in the Hamiltonian? Right? That would be cosine times the dipole. So that's the real solution. It's not so much this. It's not so much this. Is that the Hamiltonians themselves may be more complicated than you realize. So maybe it is true that wave functions are never, anything that's moving, which everything is moving, those things are never in their true ground states. But it doesn't require massive amounts of energy. The reason that things may be in that situation doesn't require much energy, and what you don't know is what the Hamiltonian is. So when it comes to, say, hydrogen atom moving, what you have to do is consider the kinetic energy, the quantum mechanics of motion. When you do the hydrogen atom, you're only solving for the electron. You're not solving for the atom itself moving around, which is a quantum mechanical calculation separate from the electronic structure. One that is almost always ignored, which is called, anyone know? It's called the Born-Oppenheimer approximation, right? So I'm just saying that's a thing to be very careful of. It's one of the most important things I can mention to you. Okay, now let me give you an example where, so I'm going to do the same thing I did, but I'm going to use notation that we've actually already seen. Let's make something a superposition of states. And let me give you, now you've seen this before. Remember what I've done is I've taken state alpha and I've resolved an identity. Now, an example could be the state is like hydrogen, and these are, okay, I don't want to blow your head off, but here's what can really happen. This is a hydrogen atom. Its real state. These are the electronic states that we solve in class. And the reason that you won't get pure 1s states, you'll get a little 1s plus a little bit of 2p. The reason that would be is because we solve this basis with a simplified Hamiltonian, but nature has a Hamiltonian so complicated we may not know what it really even is. I mean, I know that if I want to solve the real state of a hydrogen atom, I've got to do the nuclear electron part. That's what we do in class as undergrads. You've seen as undergrads. But I would also have to include the translation of the atom itself, another quantum mechanical calculation. I have to consider its potential interactions with the other mass in the universe. I have to consider its interaction with light. I have to throw that into the Hamiltonian, which would involve throwing in the Maxwell equations. And then I have to include spin-orbit coupling with the nucleus. I have to include a whole bunch of stuff to get this state correctly. Okay, so imagine that somehow I do know this, and I project onto that the 1s and 2s and 2p and 3s and 3p and 3d states that we do in our more simple, just consider the electronic state. What you would find is that because this is not quite exactly what we do in class, it's a little bit more complicated, you would find that in fact you get a 1s plus a little bit of 2p kind of description. You kind of follow me there? I know what I just said is hideously complicated, but by the end of the class you're going to get it. Anyway, so just pointing that out. Okay, that is a very complicated description, but at the end of the class, if you can think that way, then that is absolutely mission accomplished. Let me give you a more simple example. Right? Right, so you know this. Okay, that's an easier example. Right? The Sx state in the Sz basis ends up being, it's not a pure state. Right? For all the reasons that we've been talking about for like a month now. Okay, so I know that the complicated example I just gave, while true, is a little bit hard to swallow. However, I just want to point out you can do that too. I'll save my examples for this from now on. And what you're going to find, because I know I'm out of time, is that in that case, operators, expectation values, of, let's say B, we're going to say B, where B and A don't, we're going to assume that B and A don't commute, right? Just like Sx, the Sx operator and Sc operator, those don't commute, right? And that's why the Sx state is a superposition state anyway, yeah. So in this situation where you're not dealing with a pure state and you have an operator that doesn't commute with whatever basis that you're working in, then this does time evolve. So sorry I ran out of time. But anyway, so that's what we're going to do next time. So again, in the case of B being a funky operator that doesn't commute with anything, when you're looking at, if you're looking at this, let's do this, then you get no time involved. But when you do this, you will get time. This will evolve in time. Because the Hamiltonian is okay with this Z state. The Hamiltonian is not okay with these X states. So this cannot evolve in time because these are eigenstates of the Hamiltonian. Sx are not eigenstates of the Hamiltonian because they're superposition states. So this will time evolve. Anyway, that's next time. I know, oh God, sorry. Anyway, that's what I'm going to solve next time. I should have done it today. I said I got off on these weird hydrogen examples. So, anyway. Alrighty.